Hello friends, welcome to this next session on carbohydrates. In our previous session, we discussed that carbohydrates are very important molecules and they play a very important role in our life. Now today we will discuss about some important reactions and rearrangements that occur in carbohydrate chemistry. We will first review briefly what we did in our previous session. Then we will talk about the term epimers and then how epimerization occurs. Then in presence of base, monosaccharides undergo different rearrangement reactions. We will discuss about those. We will take up the formation of a special derivative from carbohydrates called Ozone derivatives. Then we will discuss the methods for increasing the chain length and then decreasing the chain length, means for preparation of higher homolog in a carbohydrate or lower homolog. And then we will discuss the method for converting aldose into ketose and ketose into aldose. And then we will summarize our today's work. In our previous session, we discussed that glucose has got 6 carbon in straight chain, 1 aldehydic functional group and 5 hydroxyl group. This was the basic structure that was given after studying various reactions. And as I said earlier that this molecule has got 4 asymmetric carbon atoms. So 16 stereoisomers are possible, out of which one represents the naturally occurring D plus glucose, and Fischer gave the configuration of glucose as this one after studying many reactions of glucose, where the position of different hydroxyl, whether they are placed to be on the right side or on the left side, this was finally decided. So this is the confirmation that was given was Fischer. We will discuss that how Fischer arrived at this configuration little later. Now when 16 isomers are possible, and in the study of stereochemistry you have studied that if a molecule and its mirror image, they are non-superimposable over each other, they are called enantiomers. If a molecule has got more than one asymmetric carbon atom, then number of isomers is more, and then those isomers which do not have mirror image relationship, they are called diastereoisomers. Now in case of glucose, if this is one particular configuration for D plus glucose, then there will be one configuration which will be exactly mirror image of it, means its mirror image will differ in the configuration at all these 4 asymmetric carbon atoms. But there are 14 other isomers which will differ in 1, 2 or 3 carbons for their configuration. They are the diastereoisomeric structures. A new term is introduced here for defining those monosaccharides which differ in their configuration at 1 carbon only. Means out of these 4 asymmetric carbon atoms, if the 2 isomers they differ at 1 carbon only, then obviously they will be diastereoisomers, but a different term is used for them and they are called epimers. So epimers are those sugars which differ in the configuration at a single carbon atom. The carbon atom where they differ is to be specified, means out of 6 carbon or 5 carbon or 4 carbon, whatsoever the number of carbon atoms are there in that particular monosaccharide, we will have to specify that at which carbon they differ in their configuration. And if the number of carbon atom is not specified, then it is considered to be C2. This is true for the case of aldoses, because in aldose number 1 is aldehyde, and if they differ in their configuration at the next carbon, then we simply use the term epimers. We do not specify the number of carbon atom. For example, D-glucose and D-mannose are C2 epimers, or we can say they are simply epimers, whereas D-glucose and D-galactose are C4 epimers. Let us see through their structures. This is the configuration for D-glucose, where the 2 hydroxyl on the lower asymmetric carbon atoms are on the right side and on this carbon it is on left, and carbon number 2 has hydroxyl on the right. If I compare this configuration with D-mannose, whatever the portion as shown in the box, you find that the configuration at these 3 carbons is same. 2 hydroxyls on the right, 2 hydroxyls on the right, and then next hydroxyl on the left. They differ in their configuration at this carbon, which is carbon number 2. And here hydroxyl is placed on the left side, whereas in case of glucose this hydroxyl is placed on the right side. So, that is why we say that D-mannose and D-glucose are C2 epimers, and as I said, if the epimerization is at carbon number 2 only, then we can avoid using number of carbon and we can simply call them as epimers. Now, if we compare this glucose with galactose, we find that at carbon number 2 both have their hydroxyls placed on the right side. Carbon number 3 hydroxyls placed on the left side. They differ in their configuration at carbon number 4. In galactose this hydroxyl is on the left hand side, whereas in glucose it is on right hand side. Again at carbon number 5 the configuration is same. So, glucose and galactose, they are classified as C4 epimers. Chemically we can convert one aldose into its epimer, and this process is called epimerization. Now, process of epimerization can be carried out that first the aldose which is to be taken, it is oxidized with mild oxidizing agent, that is bromine water, into corresponding aldonic acid, a monocarboxylic acid. And this monocarboxylic acid is treated with pyridine, and in presence of pyridine an equilibrium will be established. What happens, that I will discuss after 2 slides, that how this rearrangement actually occurs in presence of a base, but basically it is a keto-enol type of tautomerism. First one hydrogen is abstracted, and in the second step when it comes back it may take any of these phases. So, we will end up with mixture of 2 carboxylic acids which differ in their configuration at carbon number 2 only. When it is heated, so they form a cyclic esters which are known as lactone. Any of the hydroxyl from this chain, generally this hydroxyl, eliminates water with this carboxyl group forming a cyclic ester which are known as lactone, and we call it as an aldolactone is formed because it is formed from an aldose. And when these cyclic esters are reduced with sodium amalgam, then this bond breaks and one H goes to this side, this becomes aldehyde, one H goes to this oxygen, this becomes hydroxyl. So, this carboxyl group gets converted back into aldehyde. Now, in this case what happens, if we start with an aldohexose or aldopentose or whatsoever aldose is, after this oxidation we will get corresponding acid, and then on treatment with pyridine we will get mixture of both the epimeric acids, and when after formation of ester and reduction we will not get only the epimeric aldohexose, we will get starting aldose also. So, we will end up with mixture of the 2, almost half of it will be the starting aldose and half of it will be the epimeric aldose. Another thing that is very important in case of carbohydrates or monosaccharides is their rearrangement in presence of base. I discussed in my previous session that aldoses and ketoses, they cannot be differentiated by using Tollens reagent or Fehling solutions, which are the common reagent to distinguish between aldehydes and ketones. Now, why they cannot be used here? Actually, both these reagents utilize the alkaline medium. In presence of alkaline medium, they get rearranged. Aldoses or ketoses, from whichever type of compound we start, in alkaline medium the rearrangement occurs and we end up with a mixture of all these substances, that is they will have aldoses, ketoses, diols, etc. And due to the presence of that mixture, now aldoses will react with the Tollens reagent or the Fehling reagent and test will be positive. That is why aldoses and ketoses cannot be distinguished. The rearrangement that occurs in presence of base, that was studied by the scientist called Laubry de Bruyn van Eckenstein, and they studied this rearrangement in detail, and it was in 1895, long back when lot of chemistry was not known about the mechanism. Even at that time they could isolate some of the compounds and could discuss this rearrangement in detail. How this rearrangement occurs? Suppose we start with an aldose, this is an aldose. In presence of alkali, what will happen? This alkali will capture this H, this pair of electron shifts here and this pair of electron shifts to oxygen. We get this anionic structure. So, this is an keto structure getting converted into a enol type of structure, or this O minus may capture the H from the solvent, that is water, and get converted into the proper enol. So, we call it either enol or another hydroxyl is also here, we may call it as enediol structure. If this enediol structure now loses H from here to the base, this pair of electron shifts here and this pair of electron goes to carbon which captures H, and we get the ketose structure. Or if from this anionic structure, if this pair of electron comes back and this pair of electron again comes to carbon, and if this carbon now captures hydrogen from the different phase, we will get the epimeric aldose. So, we start with an aldose, we get an ionic structure, then it is an enediol structure which may be converted into ketose or the epimeric aldose. So, all that mixture will be present in presence of alkali. This shows in detail that how epimer is being formed, which I said previously that hydrogen is captured from the opposite side. If this base captures hydrogen here, now this carbon was tetrahedral before, it is a chiral carbon, but once this hydrogen is captured, this carbon is now sp2 hybridized and it is now planar portion. And now when this captures hydrogen, it can capture hydrogen from the same phase or from the opposite phase. So, if captured from the same phase, our starting compound is formed. If it captures hydrogen on the other phase, then its epimer is formed. So, if we start with D-glucose, we end up with D-mannose. But we do not use this method for the preparation of epimerization, because earlier I said in epimerization we take a longer step, first conversion to acid and then converting ultimately acid back into aldose, because here this rearrangement gives the mixture of ketose also and other products also. Suppose we start with a ketose, this is a fructose, the same type of rearrangement can occur from this side also. In presence of alkali, this carbonyl gets converted into all and this gets converted into double bond after losing hydrogen from here, that again ketonol tautomerism, we get this diol type of structure. Same diol we will get whether we start from the fructose or glucose or mannose, and now similarly they can be converted into carbonyl this side after losing hydrogen from this OH, and we may end up with mixture of glucose as well as mannose, starting ketose plus diol, all this mixture will be there. So, whenever we want to study any reaction in presence of base, it will not be a very specific reaction, because we will always have mixture of compounds in that. Then a different type of reaction occurs when these monosaccharides, whether aldoses or ketoses, they are treated with phenylhydrazine. We know that all aldehydes or ketones, they react with phenylhydrazine to form products which are known as phenylhydrazones, and in that case one molecule of phenylhydrazine is used for the one carbonyl present in molecule. But in case of these monosaccharides, aldoses or ketoses, it was observed that they react with 3 molecules of phenylhydrazine, and even some disaccharides also, they react with 3 molecules of phenylhydrazine to give solid derivatives which are named as Ozone. But these Ozone derivatives are very important for these monosaccharides, because every monosaccharide takes a different time in the formation of Ozone, and which is very specific. So, we can even sometime differentiate between different monosaccharides by just noting down that how much time it has taken in the formation of Ozone. And then crystals of Ozone for different monosaccharides are also a very specific shape. So, formation of Ozone is very important in distinguishing the monosaccharides also. Such as this is D-glucose, when this is treated with phenylhydrazine, it will react with 3 molecules of phenylhydrazine to give this type of compound, where this double bond NNHC6H5, this portion, that is a phenylhydrazine, have used up, and at 2 carbons, and actually 3 molecules of phenylhydrazine are used. Where the third molecule have gone, we will discuss while discussing the mechanism of this Ozone formation. Even if we start with fructose, this also reacts with 3 molecules of phenylhydrazine to give the same ozone, where the first 2 carbons are involved in that. Let us talk about the mechanism of ozone formation. Say this is glucose molecule. I have just taken the top 2 carbons, and obviously there are 4 other carbons. Since they are not involved in the reaction, so in order to make it more clear, only this portion of the molecule has been taken. Now this glucose, when treated with phenylhydrazine, the first molecule reacts to form simple phenylhydrazone at the carbonyl group. So it becomes CH double bond and NHPH, and this is CHOH here. Now next what happens, this undergoes a tautomerism, and this hydrogen shifts to this nitrogen and double bond shifts here. The pair of electron goes here, this pair of electron comes here, captures this hydrogen, and we get this type of structure. It becomes single bond NH, then NH and PH, and now from this NH, this hydrogen forms the nitrogen from here, forms the hydrogen bonding with this oxygen, and we get a structure which is 6-membered cyclic with intramolecular hydrogen bonding here. It gets slightly stabilized, but now it further undergoes a loss of molecule of aniline like this. This captures the hydrogen from here, this pair of electron shifts here, and this pair of electron goes here. It becomes C double bond O, and this becomes C double bond NH, and from here phenyl taking hydrogen of this OH, NH2, this is lost as a molecule of aniline. So after the loss of one molecule of aniline, we get this type of structure which is imine, and now it reacts further with 2 molecules of phenylhydrazine, one with this carbonyl and next with this C double bond NH. With the loss of ammonia molecule, we get this compound which is Ozone, and Ozone from glucose is known as glucosazone. Now this reaction is involved at the 2 carbons only. Since this hydrazone was formed at carbon number 1, and then this type of reaction has occurred, sort of oxidation you can say has occurred, this carbon got converted into carbonyl, and now again it is a hydrazone here. There are every chance that next carbon to it, which also has hydroxyl, can be oxidized and reaction could have continued further on the other carbon, but it does not undergo. Reaction occurs only at these 2 carbons. Actually, once these 2 phenylhydrazine molecules, when they are introduced, they form again hydrogen bonding and a stable cyclic type of structure. I will show in the next slide that why the reaction does not proceed further. Now, even if we start with fructose, again the first 2 carbons have been taken, we avoided writing the lower portion. It reacts with 1 molecule of phenylhydrazine to form corresponding phenylhydrazone. Then again transfer of hydrogen occurs, a tautomeric structure. This pair of electron goes here, this pair of electron comes here, this becomes double bond, this becomes NH, NH-PH, and it is hydrogen bonded to this oxygen. And again this PH NH portion, by taking this hydrogen, is lost as aniline molecule. This pair of electron goes there, this pair of electron comes here, and this pair of electron forms a bond with hydrogen. It is lost as aniline. Again we get a structure which is with 1 carbonyl and 1 imine group, and again this reacts with 2 molecules of phenylhydrazine, one with this carbonyl, loss of water, one with this double bond NH imine with the loss of ammonia, and we get corresponding Ozone. And from fructose, the Ozone is known as fructosazone, although glucosazone and fructosazone are identical compounds. Now this is the structure that is formed after the introduction of 2 phenylhydrazine molecules at the neighboring carbon, which is stabilized due to this intramolecular hydrogen bonding, and further oxidation does not occur on the 3rd carbon. It may be C double bond and NHPH. It is the hydrogen of this hydrazine forming hydrogen bond with this nitrogen, or it could be the hydrogen of this NH forming hydrogen bond with this, or both may exist. So due to this intramolecular hydrogen bonding, a stabilization occurs and reaction does not proceed to 3rd carbon. Then next we take up the method for increasing the chain. Means if we have a lower homologue in a monosaccharide, how do we get a higher homologue? This reaction occurs only on aldoses and is called as Killiani-Fischer synthesis. Again, for this reaction I have taken only the upper portion of any aldose. In the first step, addition of HCN is carried out. This HCN actually is not used as such. We use either potassium cyanide, sodium cyanide in presence of hydrochloric acid. So, this HCN adds across this C double bond O and we get the compound known as cyanohydrin, that is, it will be one cyanide, one hydroxyl. After the introduction of this HCN, this carbon now has become asymmetric carbon atom and we will get a mixture of two products. So, in a reaction we will always get a mixture of two cyanohydrins also later, but cyanohydrin which is formed is now hydrolyzed first with mild base like barium hydroxide and then acidified. This CN is converted into the carboxyl group. So, now what has happened from here to here? One carbon in the chain has been increased, which is here in the form of carboxylic acid. This aldehydic carbon which was there is now as CHOH. This is which was the second carbon has now become third carbon in the chain. Now, this carboxylic acid on heating loses a water molecule and forms the cyclic lactone. Obviously, this lactone is formed with hydroxyl on the any of the lower carbon. And then these cyclic esters or lactones, when they are reduced with sodium amalgam, one hydrogen will come to this carbon, this bond breaks and one hydrogen goes to this oxygen which becomes hydroxyl group and now this is converted into CHO. These two steps are same that we have discussed earlier in epimerization also. So, we started with this aldose, now we have obtained this aldose with one more carbon. So, this is increasing the chain length. We have increased the chain by one carbon. This synthesis is known as Killiani-Fischer synthesis. But only thing is that we will not get a pure aldose, we will get mixture of epimers. Means whatsoever aldose we start with, because this new asymmetric carbon atom has been formed here and we will have mixture of both the epimers in this case. Now, let us take this example that how this epimeric cyanohydrins are formed. This is a D-arabinose. This is the aldehydic group which was there. The lower portion I have taken in the box so that no change occurs on these three carbons. This HCN adds across this aldehyde. This becomes a new asymmetric carbon atom and it can have hydroxyl placed on the right side or on the left side. So, we have a epimeric cyanohydrins here which will be converted ultimately into epimeric aldoses. Then this Killiani-Fischer synthesis has now been modified and slightly simplified. This is an example detailed giving increase in the chain length. This is the aldehyde group. This is formation of two epimeric cyanohydrins. After hydrolysis we get two epimeric carboxylic acids. Then after the loss of water we get two epimeric cyclic lactones and then two epimeric aldohexoses. So, we start with an aldopentose, we have end up with an aldohexose, but both the isomers are there. So, this gives the full example of that. Then I said that this Killiani-Fischer synthesis has been modified and simplified, that after the addition of HCN we get the cyanohydrin. Instead of hydrolyzing cyano to carboxyl group, if it is partially reduced here in presence of palladium containing little barium sulphate which acts as catalyst poison. So, catalytic hydrogenation with a mild catalyst having some catalyst poison, this C triple bond N is only partially reduced to CH double bond NH, that is to imines. Further reduction would give the amines, but due to presence of this poison catalyst, reduction proceeds up to this stage only. We get corresponding imine and this imines can be hydrolyzed to give corresponding C double bond O group. So, we can get corresponding aldose with one increased carbon. Obviously, we will get the mixture of epimeric carbons, but the step of formation of ester and then reduction of ester, that has been changed by first reduction and then hydrolysis, which are easier steps in comparison to that. This gives a full example that suppose we start with a 4 carbon erythrose treated with HCN, we will get these two epimeric cyanohydrins. They are partially reduced using palladium and barium sulphate as catalyst. we will get corresponding imines, and it is this carbon where we are having epimeric structure, the hydroxyl on the right side, carbon number 2, this hydroxyl on the left side, and this on hydrolysis again we get 2 epimeric aldopentoses. So, this is the reaction that is used for increasing the chain length, we call it as Kleene-Fischer synthesis. Then another reaction that is used for decreasing the chain length is called rough degradation. Although there are many other methods which are used for decreasing the chain length, but this rough degradation is the easiest and most commonly used. In this case, what is done? An aldose is taken and it is first oxidized with bromine water. This aldehyde group will be oxidized to corresponding carboxylic acid, that is corresponding aldonic acid, and then it is treated with calcium hydroxide. It will form the calcium salt here. Say here in this example we have taken D-glucose. After oxidation we will get gluconic acid, and then after treatment with calcium hydroxide we get calcium D-gluconate. And these calcium salts of carboxylic acid, they are treated with hydrogen peroxide in presence of ferric ions. This is lost as a carbon dioxide and next carbon gets oxidized into aldehyde. So, the chain is reduced by 1 carbon. So, the next carbon number 2 has been converted into aldehyde. This reagent using hydrogen peroxide in presence of ferric ions is also known as Fenton's reagent. This is a mild oxidizing agent, and here it is oxidizing this group to aldehyde with the loss of this carbon dioxide from this carbon. As we have seen that whether it is epimerization or increasing the chain length, that is Kleene-Fischer synthesis, or the rough degradation, all these 3 reactions are occurring on the aldoses only. Now, suppose we want to do some process on a ketone, we want to increase the chain length or decrease the chain length, then that ketose would be converted into aldose first, carry out this reaction, and then aldose will be converted back into ketose. So, let us see how this conversion of ketose into aldose or aldose into ketose can proceed. Suppose we have an aldose and we want to convert it into a ketose with the same carbon atoms. What is done? It is treated with phenylhydrazine and we get the Ozone. The Ozone of the aldose is prepared, and then this Ozone is hydrolyzed. On hydrolysis, what will happen? This cleavage will occur at C double bond N at both the places, and we will get correspondingly C double bond O at both the places. This will be a ketocarbonyl type, this will be aldehydic carbonyl, and such structures are called ozone. And now, out of the 2 carbonyl, we can reduce easily the aldehydic carbonyl with zinc and acetic acid, and this gets converted into CH2OH. This is C double bond O, and we get a ketose structure. So, we have obtained a ketose from aldose with the same number of carbon atoms in 3 simple steps. First, prepare the Ozone, then hydrolyze it, and then reduce it with zinc and acetic acid. Then, how to convert ketose into aldose? This is a ketose. When we want to convert into aldose, first this carbonyl has to be reduced, and when reduction of this carbonyl occurs, a new asymmetric carbon atom is formed. So, obviously, we will get this alcohol group here, but it will be mixture of epimeric alcohols. So, from corresponding ketose we will get mixture of 2 alcohols here. Then these alcohols are subjected to oxidation with dilute nitric acid. Primary alcoholic group gets oxidized into carboxyl group. Then heated, loss of water, we get the cyclic lactone, and then these lactones are reduced with sodium amalgam and we get corresponding aldehydic group. But remember, when we are converting aldose into ketose, we will get one product, but when we are getting ketose into aldose, we will not get one product only, we will end up with a mixture of aldoses. So, these are the methods for interconverting ketoses into aldoses, and these were some important reactions which we come across in the carbohydrate chemistry. Now, let us revise what we have done today. After reviewing the work of previous session, we discussed what are epimers and the process of epimerization. I will briefly repeat that epimers are those isomers of aldoses or ketoses which differ in their configuration at any one of the carbon atom. We specify the number of that carbon atom, and if they differ in their configuration at carbon number 2 in case of aldoses, then they are simply called epimers. Then we discussed the base catalyzed rearrangement, that in presence of base, whether you start from an aldose or a ketose, ultimately we will end up with a mixture of product. We discussed formation of special derivatives, Ozone from aldoses as well as ketoses as well as some disaccharides, that they react with 3 molecules of phenylhydrazine to give these solid derivatives, crystalline compounds, which are called ozones. Then we discussed that how to increase the chain length or decrease the chain length in carbohydrates, and finally how to carry out conversions of aldose into ketose and ketose into aldose. So, this is all for this day. Now, in our next session, we shall take up the reactions which were actually used by Fischer for determination of configuration of D plus glucose, that is a naturally occurring glucose.